Visto che non c'è
So we can start the afternoon session. Our first speaker is Alejandro Jimenez Cano, and he is going to talk about pathologies in Earth-Hugo cosmology. Please.
Well, hello everyone. First, I would like to thank the organizers for this very nice conference. It's always great to be back in Valencia after quite a long time, and especially with this weather, which is kind of a summer in Tartu, in Estonia. Well, my talk will be basically a summary of this recent work done in collaboration with José Beltrán, Deborah Aguiar, and Tommy Koivisto on some pathologies that appear in F(q) cosmology, and well, actually they can be generalized to, one can argue that these pathologies will be essentially present generically in the symmetric teleparallel framework. So, is it working? Yeah. Nice. So, well, these teleparallel theories are constructed in the so-called metric affine framework. Basically, we include an additional general connection in addition to the metric. This connection is different from the Levi-Civita connection of the metric, which I represent with a ring over it. So this general connection will have some arbitrary in-principle torsion, the antisymmetric part, and arbitrary non-metricity, which is the covariant derivative of the metric. We can also construct a curvature tensor associated to this general connection, which is not the same as the Riemann of the associated to the metric. And a teleparallel theory, the definition, if you want, of a teleparallel framework is a situation like this, in which the curvature of the connection is vanishing. So teleparallel basically means flat, if you want, right? A flat connection. you can prove that there is for a general connection, there is a relation between the Ricci scalar of the connection and the Ricci scalar of the metric of this form, where Q and T are these quadratic combinations of the non-metricity and the torsion. There is also some mixed sector and some total derivative term, okay? So if we are in the teleparallel, we are dealing with a teleparallel theory, so the curvature vanishes, particularly the Ricci scalar vanishes. And if in addition we impose either zero non-metricity or zero torsion, you can prove that, well, it's actually straightforward, that the Einstein action is equivalent to this T or this Q, okay, up to boundary terms. This is the so-called geometrical trinity of gravity, the three different geometrical interpretations, if you want, of the same dynamical theory. Let me focus on a little bit more on this particular case. Well, not this theory, but this framework, if you want, in which you assume zero curvature and zero torsion, which is called symmetric teleparallel theory. In this context, the flatness condition tells you that the connection can always be written like this in terms of some invertible matrix lambda. And additionally, if we impose the torsionless condition, this lambda is basically the derivative of some family of four scalars. Okay, this psi. So in symmetric teleparallel, the connection has this form. Particularly, you can see that there is, for any symmetric teleparallel theory, there is a global symmetry of this form, and it's a fine transformation of this psi. And in addition, there is always, because, well, if you construct a deep invariant theory, there is always a choice of coordinates, so-called the coincident gauge. Basically, we make the coordinates equal to these functions, in which the connection, the teleparallel connection trivializes. Or in other words, you can substitute the covariant derivative of the teleparallel connection by partial derivative. So why generic symmetric teleparallel theories are expected to be problematic? Because, well, you can imagine a theory of this kind, some generic action depending on the metric and the non-metricity. Remember that Q is simply the covariant derivative of the metric. If you go to the coincident gauge, we simply remove the redundancy that we have in the theory. We will end up with an action of this kind, depends some generic dependence on the metric and partial derivatives. So since the theory is generic, in general, you will expect the 10 degrees of freedom to be active. As you probably know, there are only two possibilities that lead to a stable dynamics. The case of 2 degrees of freedom, which corresponds to a massless graviton. So in the linear theory, you will have Fierz-Pauli or WT-diff, or 5 degrees of freedom, in the case of massive gravity. So in general, if you excite more than this, you will be activating some longitudinal modes, which typically enter with higher order derivatives, and they will contribute with costs. From another point of view, you can also exhaust the gauge in the metric if you want, fix the coordinates. And if you remember that, well, Q contains Q is a covariant derivative, so it goes linearly if you want with some term, contains a term linear in gamma in the teleparallel connection, which contains something that goes with second order time derivatives of psi. So if S is a generic action with not only trivial or linear terms, but higher order terms, you will have powers of this, which in general will stay in the Lagrangian, and you cannot drop them by integrating by parts and so on. And this will lead to the theorem to ghosts in the spectrum of the theory. And as you know, these Ostrovsky ghosts are quite dangerous creatures because they propagate around generic backgrounds. The teleparallel equivalent is, of course, a special case. If you take this theory, which is quadratic in covariant derivatives of the metric, you go to the coincident gauge, you get something quadratic in partials, but that you can rearrange and write like this. And this is, you can recognize here the Einstein Lagrangian, which is basically just R to boundary term. In this case, what happens is that these higher order time derivative terms with of xi can be combined into a boundary term, so they disappear and no ghost propagate. Well, this is just GR, so nothing surprising. But if you consider other more general theories, you will have the ghosts around hidden. In particular, this is so-called newer GR. I don't like the name, but well, it's just the same Lagrangian, but with some arbitrary coefficients. Or another example is f of q, which is some arbitrary nonlinear function in general of this combination. In this case, you will have this combination, these dangerous terms in a total derivative like term, but this total derivative is inside f, so you cannot extract it, and in general, you will have some second order time derivatives of this figure. In particular, if you go to the coincident gauge, basically what you have is that the theory is some f of Einstein Lagrangian, and this is something that you cannot write as some f of r. So let me now focus on cosmological setting. In symmetric teleparallel, well, for the metric we know that the metric that realizes the cosmological principle is Riemann-Robinson-Walker metric. For psi, there are several branches of solutions depending on the spatial curvature of the background metric. In this paper, you have nicely classified all of these cases. We will focus for simplicity in a spatially flat metric. You can prove that there are only three branches for psi that are compatible with this, that we can write in this compact form with this parametrization. Okay, there is a trivial branch and two non-trivial branches. The background, to sum up, is characterized by three time functions and constants. At this point, you might think, well, you have some vector, your cosmological background, with some non-trivial spatial part. Why is this not breaking isotropy? Right? How is this realizing the cosmological principle? The point is that, if you remember, I mentioned that there is some global symmetry, some, if you want, some internal symmetry in this space of for scalars that you can use to compensate the violation of the cosmological symmetry. So if you want, this background realizes the cosmological symmetry in a non-trivial way by combining external and internal transformations. And well, here I represent the teleparallel equivalent Lagrangian evaluated in the background. And what you notice is that if you consider the general teleparallel, symmetric teleparallel equivalent, which is basically Q times the scalar volume density, you cancel this Qn, so, and this is a real parameter, so what you see is that psi only enters the action via this boundary term. So you only get dynamically the GR contribution. However, if you include some function here in front, this thing is trapped within f, so you cannot get rid of this, and you will have derivatives of psi dot, so you will have psi double dot in a nonlinear way, so you will have via Ostrovsky theorem, you will have ghosts in this theory. So what we did was to do something more explicit. Well, you see that all of this can be applied to generic symmetric teleparallel theories. We did explicit computation in f of q, because this theory was attracting a lot of attention in cosmology recently. So we took basically f of q and some matter scalar there. We did the calculation in conformal time. Also, we work in Fourier space for the spatial slices. And this is a key point. We fixed the gauge in which the connection, the perturbation of the connection vanishes. This can always be done, but this exhausts all the gauge freedom that we have. So regarding the metric and the matter, we have to keep all the other perturbations. We cannot drop any of these. So in total, we will have 4 gravitational scalars, 1 additional scalar coming from the matter, 2 vector transverse vectors, and 1 transverse and traceless tensor. For the tensor sector, this is the action that we get, where this J1 is some conserved charge in branch 1. And what you notice here is that there is one factor here in front that goes with the derivative of f. So in order to avoid the wrong sign in the kinetic term, well, the whole tensor sector action, this thing must be positive. In the vector sector, you can prove that B, one of the 2 vectors, enters as an auxiliary field, so you can integrate it and plug it back in the action. And the remaining action for E has this form. If you go to the UV limit, you get this factor in front of the kinetic term, and this should be positive in order to avoid the ghost. Something interesting also here to notice is that the action of the vector sector is proportional, goes with alpha 1. So the vector only propagates around branch 1. And finally, we took the scalars. B enters as an auxiliary field. We integrate it. We constructed the resulting action with B already substituted. We get something, well, actually quite complicated, but at the end, for our purposes, it is enough to calculate the determinant of the kinetic matrix. If you do it, this is what you get. And in the UV limit, you get this expression here. If you use the previous conditions needed for the stability of the other two sectors, you can prove that this thing is always negative. And this implies that at least one of the eigenvalues of the kinetic matrix is negative, and this implies that at least one of the scalars is Gaussian in branch 1. If we are in the trivial branch or in branch 2, this vanishes, and this implies that these some degrees of freedom are not propagating there, and this reduced spectrum is associated to strong coupling issue. So finally, the conclusion. So we found is that for generic F in F of Q, the ghost is active in the cosmological branch that I'm calling branch 1. And in the other two branches, some of these degrees of freedom that are present are not propagating around these two specific branches, and this signals a strong coupling problem. The origin of the problem, as I said before, is that there are extra degrees of freedom that are excited, and these are basically longitudinal modes of the metric. You can see them in this way. There are different perspectives depending on how you fix the gates and so on. These longitudinal modes are typically they go with higher order derivatives, and this is connected with Ostrovsky ghost. And as I mentioned at the beginning of the talk, these problems are not specific for FOQ, they are expected in general symmetric teleparallel theories. And well, limitations or little directions. Well, there are other branches. We have only focused on especially flat branches, but there's no reason for not expecting these problems also in the other branches. Actually, they are continuously connected in the space of solutions. So, and well, one can also wonder about potential Fs for which in these spatially curved backgrounds the problem is fixed, but I guess if you are interested in one of these degenerate cases, you should prove rigorously that these problems are not active. And this is basically all. Thank you.
Are there any questions?
I wanted to ask about, you said that for setting the cosmological perturbations, you have to fix the gauge. Delta gamma equals 0. What gauge? I mean, because you were saying like in the previous slide that the gamma contains time derivatives on this side. So in which sense you are fixing the gauge? Because I mean, I would say like fixing a dynamical. I mean, in F of Q, seems like is the second order derivatives in time are some sort of dynamical thing. And then in which sense you are fixing these things? Which I mean, they're not gauge. Then.
I'm not sure if I understand the question.
Yeah.
Well, for example, you have some gauge freedom, right? You have a gauge symmetry, the linear realization, if you want, of the diff symmetry, and you have some set of variables. In this case, you have this, and you have also the perturbation that you can decomp. Well, actually, you want the variation of psi. You have 4 perturbations, and you have freedom.
You are fixing the perturbations.
You are saying that basically there is some redundancy. If I write also this expanded in the, I also perform the cosmological expansion of this in irreducible representations of rotation and so on. All this set of variables is redundant, and you have gauge freedom, and you can fix it in such a way that this thing doesn't vary.
Okay, the variation.
So I mean, you are like somehow killing the higher order derivatives, but the ghost is still there. I mean, you are just moving it from one sector. And actually, we are seeing that they are maybe in here, or in here, or I mean, the ghost is still in the spectrum, even if you fix the gauge in one part.
Okay.
Thanks, speaker again. I think that So our next speaker is Ángel Jesús Macías Gil. He's going to talk about cosmological gravities in high order gravity circles. It's okay.
Okay. Well, thank you. Well, should I wear this thing? Okay. Is it on? Yes. Okay, perfect. So thank you. First of all, I would like to thank very much the organizers for all the work we bring it and for offering me the possibility of presenting this work. And today I'm gonna present some work I carried out with Javier Moreno. So as you all know, Einstein's general relativity represents our current description for the gravitational interaction, and it is given by the well-known classical Einstein-Hilbert action. Nevertheless, it is not known how to consistently quantize general relativity, and in fact, it is a non-renormalizable theory. So therefore, it is natural to search for a theory of quantum gravity. And in this regard, although promising candidates exist, and I should mention, of course, string theory, I think it is fair to say that quantum gravity remains yet to be fully understood. However, with the current gravitational wave detectors like on Virgo, the future space-based interferometer LISA, and the Event Horizon Telescope collaboration, we are at the verge of testing GR with far more precision than ever. So therefore, we should be ready for any possible deviations that may be measured in the forthcoming years. In case these deviations take place, they would occur in an energy regime above the GR palliative range, but still well below the scale in which quantum gravity would dominate, which we should associate to the Planck scale. So therefore, in this situation, in which this hypothetical situation, in which GR breaks down, but still we are well below the Planck scale, what can we do since we don't have full control of our quantum gravity theory? Then we may try to study this phenomena by adding suitable corrections to GR. But once again, which correction should we add in this regard? Well, we may adopt an effective field theory approach and add to the Einstein-Hilbert action all possible terms that are compatible with existing symmetries. In particular, in this case, the thermalisms. So, in this way, the Einstein-Hilbert action gets corrected by an infinite expansion in powers of the curvature. In fact, this is what happens precisely in the string theory. So, in this regard, we get this leading order corrections to GR up to quadratic order in the curvature, and then this motivates to define a higher curvature or higher gravity to be any theory which features in the Lagrangian this type of terms. Particular general relativity would get corrected by this term I'm showing here, where this would stand for pieces with n curvature tensors. This could be a length scale, which we can associate to the Planck scale, and it could be dimensionless couplings to be fixed by the putative ultraviolet theory. And of course, this series can be truncated to a given order, and in fact, this is what I will assume in the following. So here I won't consider any covariant derivatives of the curvature, and this should be done at some point in the future. And I'd like to say that I will use the metric formalism and the Levi-Theta connection, but of course there are other intriguing uncanonical possibilities, such as those posed by metric affine theories. So okay, some examples of these theories. Well, first of all, we could think of the most generic higher order gravity to quadratic order in the curvature, which is given by this expression, and these alphas could be the dimensionless couplings. And in particular, these terms already provide pre-normalizable actions. Another example of a higher order gravity is given by this theory here. And this higher curvature theory, which includes term of cubic coordinate curvature, turns out to provide, for instance, in this case, the most general correlators consistent with de Sitter invariance. And then another example, for instance, now in the context of string theory, we have this higher curvature gravity with quartic corrections in the Weyl tensor, which appears when we consider type 2 string theory compactified on this type of ansatz. Okay, so these are some particular examples in which higher curvature gravities, or some particular examples of higher curvature gravities. Also, the literature has mainly focused on two classes of higher curvature gravities. First, the class of log gravities, in which we correct the Dirichlet term by these combinations of antisymmetrized Riemann curvature tensors. At the quadratic order, we have the celebrated Gauss-Bonnet gravity. And the main property of this theory is that these are the most general theories which possess second-order equations of motion on top of any background. So the equations of motion are of second-order derivatives. Nevertheless, one should take into account that in 4 dimensions, these theories are just general relativity. Okay. So the second well-established example in the literature is that of bar theories, in which the Lagrangian is an arbitrary function of the Ricci scalar. For instance, making this choice, we obtain the celebrated Stravinsky's model. So in this case, the equations of motion are 4th order in derivatives, but still they are manageable. They are non-trivial in 4 dimensions in the sense that they are different from general relativity. Also, it turns out that these theories are classically equivalent to Brans-Dicke theories. So in this sense, one could argue that they do not introduce new purely gravitational phenomena. Okay. Then another example, but this is somewhat more modern. In recent years, a new class of higher curvature gravities has appeared, and it is the class of generalized cosito-polynomial gravities, or in short, GQGs. And they are defined as follows. Consider this particular static and spherical symmetric ansatz, okay? Then I define a theory to belong to the GQG class if the Lagrangian evaluator of this ansatz is a total derivative. So it satisfies this condition here. Okay, this is a priori, this seems a somewhat awkward definition. You say, what's this? Well, it turns out that this definition gives us some interesting properties. The equation of motion for this function f is at most second order derivatives. Well, it turns out that you can find theories of this type to all curvature orders and dimensions. Okay, it turns out that that the linearized equations of motion on maximally symmetric backgrounds are second order derivatives. And finally, this is perhaps the most interesting property. It turns out that any purely gradation higher theory can be mapped via perturbative field redefinitions to a GQG. So therefore, these theories form a basis for the space of effective theories of gravity. Okay. So having talked about GQGs, which feature this reduction of order for static and spherical symmetric backgrounds, well, we may think, what about studying the possibility of defining higher curvature gravities which feature reduction of order on different backgrounds? So why did you consider just static and spherical symmetric backgrounds? Let's consider different configurations which are highly symmetric, but also still with a physical meaning. And in this regard, I would like to focus here on Friedman, Lemaitre, Robertson, Walker backgrounds. Okay, and I'm going to define a theory to be a cosmological gravity if the equations of motion for the scale factor are second order in time derivatives. This is a definition. I'm going to make this definition. Okay. So it turns out, interestingly enough, that it can be proven that a theory is a cosmological gravity if and only if it is linear on the second derivative of the scale factor. This is quite interesting because you can check that by a very simple condition. You just evaluate the Lagrangian of these ansatz, and you just have to check that this is linear on the second derivative of the scale factor. So it's quite interesting. Then, and now you may ask, okay, why should I care about this theory? Well, first of all, it's fun to study this, but apart from that, it turns out that since these theories have second order equations of motion on top of this background, Then cosmological gravities produce a well-posed cosmological evolution, and in turn they allow the simple exploration of higher curvature effects on the cosmological context. But also, it turns out that these theories are appealing from the holographic context because they turn out to satisfy a so-called holographic C-theory. Let me very briefly describe what's this. So let me consider this type of domain wall ansatz, okay? Domain wall in the sense that if this function here interpolates between two ADS regions, which is recovered whenever A is linear. And then it turns out that for a cosmological gravity, one can define a function here whose derivative is always non-negative. And then this is interpreted as holographically as an argy flow between two fixed points, and therefore this was called in the literature a holographic C-theorem in this sense. Okay, so this is also interesting for the holographic context. So some examples of these theories. I mean, you made a definition that it makes sense. Do you have examples of these theories? Yes. Otherwise, I wouldn't be here. So first of all, at quadratic coordinate curvature, we have this theorem shown here, and for any dimension, it turns out this is a cosmological gravity for any dimension, and in 3 dimensions we get the well-known new massive gravity, for instance. In 4 dimensions, we have the so-called cosmological Einsteinian cubic gravity, and it is given by this fine-tuned combination of different curvature invariants. And it turns out that this here is both a cosmological gravity and a GQG in 4 dimensions. So it has second-order equations of motion on 2 different backgrounds. Okay, and then it is possible to define cosmological gravities to all curvature orders and dimensions. And in particular, an example is given in this expression, which is impressively simple because this encodes all curvature orders and dimensions. And this will be always a cosmological gravity. Okay. It turns out that these theories also possess nice features when one studies cosmological perturbations. This is quite interesting. And if we consider, in this case, scalar cosmological perturbations, which in the conformal Newtonian gates may be written this way, the perturbations are represented by phi and psi, then it turns out that you can prove that for any cosmological gravity, the equation of motion for scalar cosmological perturbations are of second order in time derivatives. This can be proven. So not only they have second order equations of motion for cosmological backgrounds, but also for the corresponding scalar cosmological perturbations will also be of second order in time derivatives. But I would like to make 2 remarks. First, this doesn't preclude the presence of higher spatial derivatives, and in fact, they will appear. They appear. And secondly, it turns out that under terms of perturbations, not every cosmological gravity will produce equations of motion with at most 2 temporal derivatives. So therefore, more research should be on this regard to study when terms of perturbations also have 2 time derivatives. Okay. So here I talk about cosmological gravities, and before I introduced very briefly the class of GQGs, question is, can you define theories which have second order equations of motion also for cosmological backgrounds and also for static and spherically symmetric backgrounds? That is, are there cosmological GQGs? This is the question. So up to quartic coordinate curvature, and in 4 dimensions, the answer was known to be yes, they exist, and some examples were studied. And now I would like to show you an example of a cosmological GQG, in this case in 4 dimensions and to all curvature orders. And for this case, this is a little bit technical, but I think it is, I have to show it. And I would like to define here some contractions of Dirichlet-Ricci tensors, okay? Some contractions of Dirichlet-Ricci tensors, some contractions of Weil tensors here, and then some numbers, okay? These are numbers, Dirichlet-Ricci tensors, and these are Weil tensors. Then the result is, these theories I'm showing here, where n denotes the curvature order, this defines a cosmological GQG to all curvature orders. So what do I mean by this? I mean that if you choose this theory, I mean, at a given curvature order, whichever, sorry, Then this theory will have second-order equations of motion for cosmological backgrounds and second-order equations of motion for static and spherical symmetric configuration. Okay. So these are the lowest order instances of these theories. Okay. Well, this is ER. This is the carbonic density in case you didn't spot it. This is the so-called cosmological Einsteinian gravity. Okay. And these three theories are unique. There are no other theories which are cosmological GQGs in 4 dimensions, okay, at these orders. Then at higher orders, there is some degeneracy. There is no unique theory satisfying this property. And here I show an example at quartic order and an example at quintic order. We observe that they get increasingly more complicated. So now, before concluding, I'd like to make an important remark here. I insist. So how should I regard these theories? Have I found quantum gravity? Am I here presenting quantum gravity? Well, I insist. Higher gravities should be interpreted from the effective field theory perspective. So in this sense, they cannot be considered as fundamental theories. They are not fundamental theories. They're a tool to capture corrections to general relativity. So in fact, it is expected that these theories will be non-unitary and they will suffer from strong coupling issues. But the important aspect is that these problems are not present if we stick to an EFT approach, which is the approach that one should adopt when studying higher order gravities. These are not fundamental theories. So there's no need to save these theories. They are, since they should be considered from the effective field theory perspective, it is okay. However, having said this, I think it also makes sense to study exact solutions in this classical effective field, in this higher chromatographics. Why? Why? Because it is theoretically appealing to have at disposal exact analytic solutions. That is, since we can perform analytic computations, then let's do it. Secondly, because then one could always truncate or perturbative order if desired. Okay. And then finally, this is a little bit speculative, but anyway, I think because then explicit solutions may showcase novel interesting features, which one may somehow interpret that they are due to quantum corrections, which perhaps cannot be captured perturbatively. Okay. So in conclusion, higher chromatographies arise when we want to incorporate quantum corrections to GR. However, beyond Lovelock, these theories always involve equations of motion with 4 derivatives. However, it turns out that some classes possess second-order equations of motion on specific backgrounds, not always, but on specific backgrounds. And here I've talked about cosmological gravities, which possess second-order equations of motion for cosmological configurations. I've told you that they exist for all chromatic orders and dimensions. It turns out that these theories provide equations of motion which contain no more than 2 time derivatives for scalar perturbations. And finally, I've also told you that a subset of them also possesses second-order equations of motion for static and spherical symmetric patterns. So thank you.
Any questions?
I
Wait,
have a question.
behind you.
Me first.
No, there first.
Just a curiosity, you said that this consists of logical terms, and this is for the all EFT operator?
I didn't understand the question. What do you mean?
Yeah. So at some point, I think you said that you can construct a basis of the EFT operator with these consists of logical terms.
Yes.
Is that true even if you include covariant derivatives of the
Up to 10th derivatives, yes. For derivatives higher than 10 derivatives, the answer is not conclusive because there's no. It is a little bit difficult to prove that beyond 10 derivatives, but I mean, up to 10 derivatives, the answer is yes. Higher than that, we don't know.
So you're saying that all the EFT, so all the quantum corrections up to that order can be expressed in terms of powers of the ring without no derivatives.
Yes. Yes, so what I refer is the following. So what I refer is the following. Well, hold a second because this is the. So these GQGs are defined according to their properties when they are evaluated on static and spherical symmetric patterns. Okay, so the statement I said before refers to the fact that those terms with covariant derivatives wouldn't affect static and spherical symmetric configurations.
Okay, so the statement is only for those parts.
No, that's hold a second. No, hold a second. So these theories are defined according to the properties on this part. And it may turn out, I mean, there's no blackboard here, but it turns out that you may consider a certain theory which does not contribute to the equations of motion for static and spherical symmetric patterns. Okay, I mean, you can think of some curvature invariants. I don't know. Okay, I don't know if I can do this, but okay. Imagine. So, for instance, well, I know you can see that. Okay, then. Okay, then. Okay, so there are some curvature invariants which. Okay. Okay, so I mean, for instance, I don't know if it is. I can define these combinations of curvature invariants. Okay, well, I mean.
Yes.
Okay, perfect. So 1 second. This is. So for instance, this in 4 dimensions, this is the trace derivative tensor. Okay, so this trace derivative tensor, if I consider this combination, this is identically 0 for the static and spherical symmetric configurations are both. So therefore, this would be a GQG, but this doesn't affect the equations of motion. So this is trivially GQG, but this doesn't affect the equations of motion. So what I'm saying that up to 10 derivatives, there will be terms of this form with covariant derivatives, let's say, which doesn't contribute to the equations of motion, and on static and spherical symmetric backgrounds. And therefore, these theories will also appear in my effective field theory expansion. So therefore, what I'm saying is that up to 10 derivatives, those terms with covariant derivatives will be trivial when evaluated in static and spherical symmetric background. That's the statement.
But not in general.
Not in general. Yes.
We have time for our last no blackboard question.
There you go. Okay. Thank you for interesting talk. I guess you just established the framework for high order curvature gravity. You didn't solve the perturbation equation for this gravity. You didn't solve the perturbation equations.
In this work, I haven't solved any equations. Is that the question?
Yeah.
I haven't solved any equations. So this was just studying which theories possess equations of motion of a certain degree in derivatives. But I haven't solved any equations. There are some works in the literature in which they pick a specific curvature order and they study this equation and obtain solutions perturbatively or numerically. But here I haven't presented anything about solving equations. That would be a future direction.
Yeah, because I'm working on testing this fundamental physics with data. So I'm I very much care about to test the signal of this gravity. So I hope you can solve it.
Yes,
Maybe you can.
It can be done. Hopefully, yes, we'd like to do something in the future. Thank you.
Yeah, thank you.
Last time again on speaker. Hello. So our next speaker is Jose Perdiguero Garde. He's going to talk about cosmological solutions in polynomial affine gravity. So when you want. This is just for the audio or for I can use? Yeah, okay. In your pocket. Okay, thank you. Okay, thank you so much for the opportunity to share with you my work related to polynomial affine gravity. And let's just go straight to the point. Okay, so what is polynomial affine gravity? Well, it is an alternative gravitational model where the gravitational interactions are mediated exclusively by the affine connection and not the metric tensor. Okay? And also, when we build the action for this model, we only use the irreducible fields of the affine connection, and the metric tensor does not play any role at all in its formulation. So in that sense, this is a purely affine model of gravity. And I just want to emphasize that the metric tensor does not play any role at all when we build this model. Okay? So how do we build a model? Well, to build a model, we need something like a building block. And our building blocks, we get those from the affine connection. And what we do is that we take the affine connection and we separate it into the symmetric and antisymmetric part. The symmetric part, which is the first term, allow us to define the covariant derivative, whereas the antisymmetric part is related to the torsion tensor. And the torsion tensor, we decompose it into its irreducible fields, which are the A and B field. The B field stands for the traceless part, and the A field, it is the vectorial part of the torsion tensor. Okay? And also, we want to preserve the invariance under diffeomorphism, which is why the symmetric part of the affine connection goes to the action indirectly through the covariant derivative. And as I said earlier, we do not want to use the metric tensor at all when we build this model, which is why the volume element that we use here, it is defined only by the wedge product. Okay, so our building blocks will be the A and B field coming from the antisymmetric part of the affine connection, the covariant derivative coming from the symmetric part of the affine connection, and the volume form, which is defined completely by the wedge product. So now that we have the building blocks, how we actually build the action? Well, what we do is something like a dimensional analysis technique. And what we do is that we define two operators, then and the W operator. The N1 counts the number of free index. So in our convention, it is a +1 for every upper index, and it is a -1 for every lower index. So when we apply these operators to our irreducible fields, we have this expression, and the W operator counts the weight of the object. Okay, so the only object that has a weight, it is the volume element, the volume form. Okay, so we have the building blocks, and we have these two operators. An arbitrary term is defined by m times the A field, n times the B field, P times the covariant derivative, and Q times the volume form. Okay, so if we apply these two operators to this general term, arbitrary term, we get this result. And because we want to build scalar densities, we need to impose the constraints that Q must be equal to 1. And because these are scalar densities, the number of free index of the object must be equal to 0. Okay? So what we do is that we replace Q equal to 1, then move the 4 to the left-hand side and multiply everything by -1. And what we get, it is a constraint equation. And this constraint equation tells us all possible, well, all the solutions to the constraint equation tell us all the possible terms that can go to the action. Okay, so basically what we have here are 15 different branches of terms that can go to the action. But also we need to keep in mind that this is the structure of the term. So every term can have at least maybe at least like 5 or 6 permutations, because what we need to do is to build every single possible contraction, and also we need to keep in mind the symmetries of the object. Okay, so what we do is that we take these 15 branches and study all possible permutations, and once we do that, we get the action. And the action, it is this one. So this is the action of the polynomial affine gravity in 4 dimensions, and it has 20 terms. And there are some nice features about it. Okay, so first of all, it preserves the invariance under diffeomorphisms just by construction. And also, it has this property that we call rigidity. And what I mean by that is that because of the absence of the metric tensor in our formulation, we have a finite number of terms that can go to the action. Okay, and this is not something that usually happens in metric affine theories. So because of the lack of a metric tensor, we have a finite number of terms that can go to the action. Additionally, the coupling constants are all dimensionless, which suggests, and this is speculative, that there is some sort of conformal invariance, and also it is power content renormalizable, which is a necessary condition, but not a sufficient condition to say that this model it is renormalizable. But we know we are on the right track. And in the hypothetical scenario where we want to obtain a quantum version of this action, all possible counter terms will necessarily have the form of the ones that are already written here, because of the constraint and because we do not use the metrics. Okay. Well, in the torsion free sector, we can actually recover all Einstein vacuum solutions, which is nice. And also, even though we start with a purely affine model, we only endow the manifold with an affine structure. We can still have 2 metric tensors coming from the symmetric and the antisymmetric part. So the Ricci tensor comes from the symmetric part of the affine connection, and this P tensor, which is called the Poplawski metric tensor, comes from the product of 2 torsion tensors, which is the antisymmetric part of the affine connection. Okay? And interestingly, we can actually couple a scalar field in this model without the use of a metric tensor. And we can use this scalar field to generate inflation in our model. Okay, so we have the action, we have some nice features, and right now what we need to do is to vary the action to obtain the field equations. And we have 3 irreducible fields. So if we vary the action with respect to the gamma field, which is the symmetric part of the connection, these are the field equations. And this is just a picture, I didn't write this. And if we vary the action with respect to the B field, these are the field equations. Fun story, I actually varied the action by hand because I didn't know how to use any software. So this took me a while. And these are the field equations for the I field. Okay, so we have the action, we have the field equations, and we want to do cosmology. So we need to build an answer for the affine connection that is compatible with the symmetries of the cosmological principle, which are isotropy and homogeneity. And how do we do that? Well, we use the Lie derivative, and we compute the Lie derivative along the Killing vectors that generate the symmetries of isotropy and homogeneity, which are translation and rotations. And this is the expression for the Lie derivative of the symmetric part of the affine connection. And if you notice, there is an extra term right here This is because the connection is not a tensor. Okay, so it doesn't transform as a tensor, and it has this non-homogeneous term. Okay, so we compute the Lie derivative, and this to find the answer that is written right here, we need to solve like 64 differential equation, but this is the final form of the answer. And what we found is that the symmetric part of the connection, it is defined by only 3 time-dependent functions. However, the first coefficient is in red, and that is because under a time reparameterization, we can actually vanish the first term, and we can repeat the same idea for the B field and the A field. And the final structure of the cosmological answer, it is written right here. So the symmetric part of the fine connection only depends on two time-dependent functions. The B field, which is related to the torsion tensor, only depends on one time-dependent function, and the A field only depends on one time-dependent function. Okay, so we have the answer, we have the field equation. What we do now is that we plug the answer into the field equation, and what we get is this. So this is these are the dynamical equations for the polynomial affine gravity in the frame of cosmology, and these are 5 differential equations for 4 unknown functions of time, and we need to solve this. And actually, we can solve this, and we can find an exact solution to this problem. And to see this, well, I don't know if you can see this, but the first equation has a structure of something times C equal to 0, and the second equation has a similar structure, another something times D equal to 0. So that tells us right away that we have 4 different branches, and we can study every branch, and we can solve this and find an exact solution. And the exact solutions are right here. So H is like something 1/T, D is something like a power law solution, C also like a power law solution, and the last one, vanish. And alpha, beta, and gamma are related to the coupling constant. Okay, so we have the solution. What can we do with this? Well, we have an idea. In standard cosmology, we have 2 fundamental fields. We have the metric tensor, and we also have the energy momentum tensor. Okay, whereas here we have the Ricci tensor, we have the Poplawski tensor. So we can play this like a similar idea between those type of gravity formulations, and the C function that defines the torsion could play an analog role to the energy density, and the Ricci tensor allow us to define a fine scale factor. So what we do is that we can fix the parameters alpha, beta, and gamma to find the explicit, well, it's not explicit, but to find well-known solutions in general relativity in this context of polynomial affine gravity. So we can actually emulate radiation era, non-relativistic matter era, and we can find constraint to have an accelerated expansion. So to finish this presentation, I just want to highlight that we use the torsion tensor to emulate an energy momentum tensor, and the torsion tensor acts like a source of matter in this type of affine gravity. Okay, and that's it. Thank you for your time. Question time.
Just is a curiosity. Did you try also not doing only cosmology, but other kind of tests? It's interesting, no? The idea to let's say mimic something.
Yeah, like emulate something. Yes, well, at the moment we are currently working with spherical symmetries, but we want to start with something much easier. And in cosmology, we have 6 scaling vectors. So we have a lot more constraints on the answer that if we want to do some spherical symmetry, which only has 3 Killing vectors. But we are working right now.
Hi, and thanks for your nice talk. I wanted a short question. Could it be like imposing the Lie derivative of the connection equals to 0 be incompatible somehow with some of the connection equations?
Connection equations?
Yeah, because you show like a lot of equations of motion for the connection, and then you impose like the Lie derivative of the connection equals to 0 for some symmetry. Could it be possible that this is incompatible with some?
Well, I think at least when I derived the explicit form of the Lie derivative of the connection, what I did is that, well, basically I compared 2 vectors living in different tangent space and moved one from one point to the other by a coordinate transformation, and that induced the non-homogeneous term. But in that process, I never used the metric tensor.
Okay. Yeah.
So I think.
So there's a question online.
But I think it's okay.
Okay, nice. Because in our cerebral approaches, there is also people imposing like the Lie derivative of the connection equals to 0. It's just the connection has much more restrictions in our models. But at some point it happened that someone found them.
But with the same
with metric. I mean with metric and connection, and then they impose the Lie derivative on both terms.
Right.
And then there was some sort of problem there.
Okay, but what I can't do is upper and lower the index line. That's something I cannot do.
Yeah, I know.
It's not allowing this.
Yeah, I know. Because another.
Yeah.
Thank you.
Well, I am very grateful for the possibility to participate and to make a question. So my question will be the following. In principle, we know that all gravity theories have some difficulties. Renormalizability, many theories are non-normalizable, ghosts, etc. What are the difficulties of the affine gravity in comparison with the Einstein gravity? What are the problems which, by your opinion, have faults, have problems within the affine gravity?
Okay. At the moment, we haven't studied yet if there are ghosts presented in this theory. And actually, we haven't done yet the perturbation model because in standard general relativity, one perturb the metric tensor. And here you have to perturb the affine connection, we have another index. So it's not something quite trivial or straightforward to do that, but that is something that we are going to do. That's why I'm here. So I think it's finished. So we move on. And thank again our speaker.
Yeah.
Our last speaker for this afternoon session is Adrian Casado-Gurion. He's going to talk about junction condition and application in scalar Poincare gravity.
Thank you. Thank you so much. Well, so as the chair said, I am Adrián Casado-Gurion. I'm a postdoc at Complutense University in Madrid. And of course, I'm going to talk about this work on junction conditions in biscalar Poincare gravity. Here, well, done in collaboration with Álvaro de la Cruz Lombriz, Alejandro Jiménez Cano, and Pepe Maldonado Corrado. And here in this work, we didn't just obtain the junction conditions in this theory, but we also clarified some issues, some subtleties present in the junction condition formalism, which are important for higher order theories of gravity and for metric affine theories of gravity. So, well, with this talk, I want to convince you of the importance of junction conditions for the description of compact objects and, well, their various applications in gravity in general, apart from presenting these junction conditions. So, just to start, why are junction conditions important and what are they, of course? So, nowadays we have a lot of proofs of gravity. Most of them come from observations of compact objects. And when we have a typical compact object, we usually need to glue together two different solutions of the theory we are considering. We can think, for example, of a star, okay, which ends at the gluing surface, where we glue the interior to the vacuum exterior. But of course, the compact object can be, for example, a wormhole supported by a thin layer of matter living on this matching surface, which we call sigma. Okay. So when we do the gluing, we must make sure that the matched solution is built consistently, and also that's why we need to impose these junction conditions, which will also determine which kind of compact objects are possible in a given theory. And of course, because they are related to this matching surface and the evolution of this surface, these junction conditions will also determine the dynamics of these objects. For example, they will be important in collapse. So, how do we glue two spacetimes together? So we start with our two basic spacetimes we want to glue. And the first thing we have to do is to cut them, because maybe we do not want to retain the whole spacetime in the gluing. For example, think again of a star. We want to keep only the part up to the radius of the star. So we have to cut the spacetimes to separate the matching surfaces, okay, dispose of the parts we want to forget about, and then keep only the parts that we really want to do. Of course, these two matching surfaces, one in each of the two spacetimes, are the matching surface, the unique matching surface, and thus they must be identified through a diffeomorphism. And once this is done, all we have to do is to choose our favorite brand of glue and paste both spacetimes together in such a way that the complete matched spacetime is the disjoint union of the plus part, one of the sides, the minus side, and sigma, which is part of neither the plus or minus sides. So, because, of course, we are dealing with geometrical descriptions of gravity, we are interested in studying the geometry of sigma. And the geometry of sigma is characterized by four essential quantities. First, we have the normal vector sigma, which, well, by convention, points from the minus side to the plus side. Then we have the tangents to sigma, which are defined in this way, in terms of these two coordinate systems, one which covers sigma and its surroundings in both sides, and another which is intrinsic to sigma, and thus three-dimensional, where we use these Latin names. Of course, we are trying to deal with time-like and space-like hypersurfaces, and this can be parameterized by the epsilon parameter. We will not treat the null case, which is much more complicated and requires its own formats. Then the two main geometrical quantities for sigma are the induced metric, constructed in this way using metric and vector, and the extrinsic curvatures of both sides of sigma, which are different because in principle the connection does not need to be continuous across sigma, and thus we have two different derivatives which make no space. So, Once we have constructed our glued spacetime, we know the properties, the geometrical properties of our glued, of our matching surfaces, sorry. We want to do physics. And if we want to do physics, we have our theories with their dynamical fields, with their equations of motion. So there's a problem here. If we have two solutions with their field contents, and we try to glue them, in principle, these physical fields could be potentially discontinuous across the matching surface. And therefore, their derivatives will be undefined. This problem can be solved by using tensor distributions. That is, we assign to every tensor a distribution, which we denote with an underline. And when we have done that, it turns out that we can compute the distributional derivatives of these tensor distributions, because this distributional derivative is well defined in terms of its action on some test tensors living on the glued space. For this reason, all we have to do is to go to the action of the theory, identify the basic fields, the dynamical fields that appear there, assign to them a distribution which consists of a part which lives only on one side, a part which lives only on the other side. This is given by these theta distributions, these Heaviside distributions, which are the equivalent of the usual step functions of the group. And then plug them in these distributions into the equations of motion. And we're going to find various derivatives, which are going to give us derivatives of these jump distributions. These first and second derivatives can be computed using the delta distribution, which is essentially the derivative of the Heaviside step distributions. And using this definition of the distributional derivative, we can compute further order derivatives. With this, what we clearly see here is that every time we do a derivative of these basic fields, we are going to get higher and higher order derivatives of the delta function. For example, here with one derivative, we get the delta. With two derivatives, we get the derivative of the delta and terms proportional to the delta, etc. This means that in general, if we have a field theory and we compute the distributional version of the field equations, what we are going to get are terms of this schematic form. Rho plus delta sigma, delta star, sorry. Where rho is what we call the regular part of the distribution, which is the part that goes only with these Heaviside distributions. And the singular part is a collection of terms, delta 0, delta 1, delta 2, etc., which contain higher and higher derivatives of the delta. For example, here, this term delta 0 is proportional to the delta. This one is proportional to the first derivative of the delta. This one is proportional to the second derivative of the delta, etc. And we call them monopoles or thin shells in the case of delta 0. In the case of delta 1, we call it dipole or double layer. And in the case of delta 2, quadrupole, delta 3 would be the octupole. The reason why we give them this very physics, these names full of physics will become apparent soon. So we now have our distributional equations with their well-defined derivatives. Now we have a problem. In the case of distributions, derivatives are well-defined, but products are not in general, except in some very simple cases, some of which, such as this one or this one, require some prescriptions, which are, well, explained here in our paper. If you want more detail, you can go there to check all the subtleties that appear when defining these products. And because in general, other products apart from this will be undefined, we must impose conditions that make sure that those products do not appear on the field equations. And these are precisely the junction conditions. Apart from that, we will also have another set of junction conditions, which will give us physical interpretations of the well-defined distributional terms that are left on the equations, because we are going to get well-defined distributions. What do they mean, those distributions? So, all in all, to sum up, what do we have to do to get the junction conditions in any theory of gravity? So, or any field theory, not necessarily of gravity, like this is valid in every case. So first we have to expand the equations of motion in terms of the basic fields, including the metric, it's dynamical in the theory. Then we have to promote these basic fields and their covariant derivatives to distributions, as I showed you before. And then we have to remove all undefined products. This will give us a set of what we call consistency conditions. This will be our first set of junction conditions. Okay, we have to remove one of these terms, delta times delta, etc., which are undefined. Then, yes, we have after we have all consistent field equations in the distributional sense. Now we have to give an interpretation to the well-defined distributions that we have. And it turns out that to interpret these distributions, all we have to do is to move them to the right-hand side of the equation. That is, to interpret those distributions as describing sources that live on the matching surface sigma. Why? Because, of course, these distributions that I showed you here, these ones, are only well-defined on sigma. And it turns out that actually these names characterize what these types of terms describe. For example, this term is called the monopole because actually if you go to a gravitational theory where you have these kind of sources on sigma, they will describe a matter distribution, spin distribution, etc., living on sigma. And the same with this ones, they will describe dipoles and so on. So this is the physical interpretation. But of course, sometimes we do not want to have these sources of sigma. For example, if we have a star, we want to start at the end and then give way to vacuum without having a thin shell living on the surface of the star. This is why we have to impose an additional set of junction conditions if we want, which is the smooth matching conditions, which remove all these surface sources on sigma. Okay. Well, so for example, just very briefly, how do we compute the junction conditions in GR, for example? So the consistency conditions, which make sure that the connection and the Riemann tensor are well defined as distributions, are simply the continuity and the regularity of the metric. Here, we are introducing this notation, these brackets, which means the discontinuity across sigma. So the discontinuity is equal to 0. Then this is continuous, what is inside. And then remember that this delta star means the whole singular part with all its sectors. In GR, the equations of motion give rise to a singular layer condition, which is this one. This is a thin shell of matter, a monopole of matter, which is proportional to the discontinuity of the extrinsic curvature. So if we want to make this vanish, then we have to impose that the extrinsic curvature is continuous as well. So now that we have reviewed the formalism, let's go to the particular case of Poincare gauge gravity. Remember that up to now, everything I've said is completely general for any field. So what is Poincare gauge gravity? Well, we know that apart from gravity, all other fundamental interactions of nature are described using the gauge theories. And of course, it would be interesting to find a gauge theory which would give us gravity. In particular, if we want to do so, the natural candidate for the gauge group of the theory would be the Poincare group, which gives rise to these two field strengths. For translations, we have the torsion tensor, and for Lorentz transformations, we have the Riemann tensor. Therefore, Poincare gauge theory of gravity is a metric affine theory with independent metric and connection. The only thing is that the connection is metric compatible, but has torsion and non-metricity. Then we build the most general quadratic action in these two field strengths, which gives rise to this action, which of course can give ghostly instabilities. So these instabilities have been removed here in this reference, and we are left with this action, which gives us the most general ghost-free quadratic Poincare gauge gravity theory, which we call biscalar Poincare gauge gravity theory because it propagates two scalar degrees of freedom apart from the usual gravity of GR. Here, this theory depends on the torsion vector, the torsion axial vector, the pure tensor part of torsion, which vanishes dynamically, so we will forget about it in the remainder of the talk. And as you can see, it contains terms which go with the Ricci scalar squared, the square of the host pseudoscalar, which is this contraction of the Riemann tensor, and then mass terms for the torsion pieces. So, as you can imagine, this theory has complicated equations of motion. Here they have been simplified in terms of something which is very long and didn't fit into a slide. So, of course, this does not look as intimidating as the equations of motion we have just seen in the previous talk. But of course, these are complicated. All I want you to know from these equations of motion is that, of course, this theory, despite its appearance, is well motivated. It's a gauge theory of gravity, and it has three matter sources. Okay. These L and J will be the sources for torsion. They are spin currents, and then T mu nu is the standard stress energy tensor, which sources the metric. So now, no matter how intimidating a set of equations of motion looks, if you follow the procedure that I showed you before, you can straightforwardly compute the junction conditions with a little bit of time and patience. And what we have found in the case of Poincare gauge gravity is the following. First, we get these consistency conditions, which are the same as in GR, continuity and regularity of the metric, to have a well-defined Levy connection. To have well-defined torsion products, that is, terms that go with two torsions, the two torsion vectors. To avoid these undefined products of singular parts, what we have to do is to require the torsion vector and torsion axial vectors be regular, have vanishing singular parts. And to have well-defined metric equations, we get this set of four conditions, which are all of the form parameter times discontinuity. So remember that in the action, we have several parameters. For example, we have this beta that goes with the square of the Ricci scalar, and this alpha that goes with the square of the host pseudoscalar. So depending on the values of these parameters, we can have several sub-cases inside this theory. So, for example, if this beta vanishes, then we do not need to have a continuous trace of the extrinsic curvature. But if we have this term in the action, then we need to have a vanishing trace of the extrinsic jump of the trace of the extrinsic curvature, similar to metric f of r gravity. And also we get these extra consistency conditions, which depend also on the subcase we are dealing with. So now that we have made the theory consistent, we proceed to interpret the well-defined distributions that are left in the field equations as as singular layer contributions living on the matching surface. And in particular, we find something very interesting, which is the presence of spin monopoles on sigma. That is, thin shells of spin, which are proportional in this case, as you can see, to the jump of the Ricci scalar and to the discontinuity of the host pseudoscalar. So whenever we have discontinuous R or H, we are going to have spin monopoles living on sigma in any matched configuration in this theory. Another very interesting thing is that we have stress energy double layers living on sigma. That is, we have a matter dipole living on the matching surface if the Ricci scalar is discontinuous or if theta is zero. This is very similar to quadratic f of r or quadratic theories of gravity in general. And it's very interesting because first, this does not appear in GR. And apart from that, the existence of dipoles in gravity is something which one does not expect, because we think that gravity is attractive, then we would not expect dipoles to occur in gravity. But this is well known that quadratic gravities feature this sort of dipoles when matching, and this is the case here too. And finally, we have a stress energy thin shell matter monopole, which is given by a long expression, which is it's not necessarily put it here because this is similar to GR but much more convoluted. And finally, of course, if we want to remove all these sources, we have to impose these smooth matching conditions. For example, the continuity of the trace, the continuity of the extrinsic curvature, similar to GR. This one, for example, is similar to f of r. And this one too, the continuity of the Ricci scalar and its normal derivative. And of course, the continuity of the whole scalar, which is not present either in GR or in f of r because they do not have torsion. This is similar. So as you can see, there are more constraints than in GR. So having two smoothly glued solutions in GR in biscalar Poincare is much more difficult than in GR. So just to sum up and some future prospects. So, well, I hope I have convinced you that junction conditions play a crucial role in the theory of compact objects in modified gravity, because they make the solutions mathematically consistent, and they can govern the dynamics of the surface of these compact objects. So they are very, very important. With our derivation of the junction conditions in Poincare gauge gravity, we have clarified some subtleties. Please, I refer you to our paper if you want to take a look at them. And we have introduced some standardized notation and terminology, which is valid for every theory. So if you want to compute the junction conditions in the theory that you prefer, you only have to follow our prescription. And what's the physical relevance of all of this in the case of Poincare gauge gravity? We have seen first that we can have effects coming from torsion, which is something very new. We can have torsion thin shells. That's very interesting. This is because we have, well, I have said this in a different order, but we have a richer singular structure. Okay, we have these torsion thin shells, and we have also these matter double layers. This can give rise to more varied solutions describing wormholes or other match configurations where we do not have this smooth matching. The case of smooth matching would be much more complicated here in these theories because of the tighter constraints. And we know that, for example, in metric FFR, this gives problem with collapse, for example, which is much more constrained. But this would give rise to possible observational constraints because we expect to find solutions which are much more different than those we have in GR. And that's all. Muchas gracias. Thank you. And if you have any questions, please.
Any questions?
Thank you very much. There's an old joke that says at the end of almost every talk on junction conditions, there's one question that comes up. So let me today be the awkward person who answers that question. Did you consider null shells?
No, we didn't. We didn't because the formalism is a bit different. I mean, it is not that you cannot construct the junction conditions in the null case. It is a bit different, and most cases of physical importance, such as stars, for example, or wormholes, require time-like surfaces. So, but yes, it could be done. It would be a bit more complicated, but the thing with junction conditions is that everything is straightforward, although it might be computationally a bit hard, but it could be done. Yes, for the future, it would also be another prospect.
No, I can ask. No microphone.
It's for the web.
Okay, thank you. Several years ago, and when I was a PhD student, I calculated the wormhole solution by using the junction conditions. If I understand your work correctly, so you made progress in this field. So if you use your junction condition, if we use your results, what will be different to calculate a wormhole solution?
Well, for example, because we have more varied matter sources in sigma here. In this case, you can support your wormhole not with exotic matter, for example, but with torsion. For example, that would be a very interesting thing, like to find wormholes filled with torsion. Also, apart from that, here, you know, hidden in these long expressions are, well, this continuity of the Riemann, Ricci, etc. So if you want to find a wormhole solution which adapts to your needs, then you have also more combinations of parameters and of discontinuities that you can play with, etc. And also this in Poincare gauge gravity. In other gravity theories, the problem comes that when you do the distributional field equations, you usually have higher order derivatives. So what we have done is to clarify how to do, well, give a systematic procedure on how to compute that, like the precise expressions for the thin shells that then will appear in the wormhole, a systematic procedure, and also some prescriptions for these undefined products. Because, for example, this product in principle, in which you have like some regular distributions and one monopolar distribution, this is undefined. The thing is that you need this in physical theories because these kind of terms appear on your field equations. So you have to give a prescription on how to multiply these distributions according to some physical principles. So that is also like the other part that with this formalism, you are sure that you're building something consistent, which then you can use to model wormholes or any other solution.
Thank you for updating my knowledge.
So let's thank Adrian again.
Thank you.
Now we have time for a break, and we see here at 5:30. They told me to see you at 5:20. Well, say so.
Is there coffee?
It's a break, but not coffee. We can go to the cafeteria.
Que tiene otro nombre.
La noche
Sí.
trae el aire frío.
Claro, ese término.
for having me here. It's a pleasure to be here. As Nico said, I'm Claudio Lazarte, a PhD student, 2.5 PhD student of the Department of Astronomy and Astrophysics of this university. As you can see, the title of my work today, my talk today is L-Brock stars towards more complex exotic compact objects. And as well as you can see, there is a field of National University of Toronto from Mexico, because the first part of this work was performed there in my master research thesis. Basically, we propose a new model of Broca star that I'm going to be sharing today. Basically, we studied this system numerically, and the first part of this study was trying to get initial data from spectral methods, and the second part was based on running evolutions in the cluster of this university, in this cluster, and we are happy that now we have some results, preliminary results to show. I forgot that I work here with Nicolas Sánchez-Gual and José Antonio Font. Okay, so let's begin. First, to try to answer what L-Brock stars are, we have to review briefly some concepts about bosonic stars. Well, bosonic stars are considered as self-gravitating objects that the matter content is formed by one single or several complex bosonic fields that have very well-defined harmonic time dependency given by this complex factor with this time frequency omega, and specifying the nature of the bosonic field, we can have scalar boson stars with this scalar field ansatz, or vector boson star, aka Broca stars, with this Broca potential 1 quarter. These kind of systems are particularly just focusing in the case of bosonic stars with space-time, with a static space-time, okay? And in the case of the Broca stars, we have this potential with just these two components, the time and the radial component, as we can see, and these systems are spherically symmetric, everywhere regular and horizonless, and can achieve masses and compactness similar to the black holes. In 2018, Miguel Cubierra collaborators present a generalization about these systems. They present a kind of generalization based on multi-field bosonic stars with angular momentum, and they apply this generalization to the case of L-boson star, to the case of bosonic stars. So they name this system, this new bosonic star, as L-boson stars, where they form 2L+1 scalar complex fields. But in this case, those fields have an angular dependency given by spherical harmonic functions, and with the same L number, angular momentum number, and all the values of this magnetic number available for the same L. So this system, these fields have the same radial profile and are coupled gravitationally, minimally coupled gravitationally, such that they produce a space-time that have spherical symmetry. Despite that, the constitutive fields have angular momentum given by this dependency of the angular variables or coordinates. In my work, in my master research, we extend the applicability of this generalization to the case of the vector boson stars, I mean the Broca stars. That's why I present the L-Broca stars when we join these 2L+1 Broca fields, and we propose this ansatz that is a bit different from the original ansatz for the case of spherical symmetry with just one field. And as we can see, in this case, we have angular components in the potential form, and the angular dependency of these angular components are not given by just spherical harmonics, but in this case, we have angular derivative of the spherical harmonics. And we have to introduce a new radial profile function to obtain a self-consistency and evolution equations with the constraint equation of the system. So with this ansatz,
we can form a new Broca star with spherical symmetry in the space-time. Okay. Now, why we have to study these systems? Well, basically, there are several works that show that Broca stars are black hole mimickers. So they are viable candidates to deal with the problem of the inerrancy in the interpretation of strong gravity data against the black hole paradigm. For example, I mean that we could consider gravitational waves that can be interpreted as a merger of Broca stars. In that direction, Juan Carlos Bustillo and Nicolás Sánchez-Gual and collaborators presented a work when they showed that the gravitational wave signal 190521 can be considered as a merger of Broca stars. Even they propose a new potential vector with this ultralight mass. So, with this motivation to study Broca stars, what we look for is more complex Broca stars to try to imitate some kind of real scenarios. Okay, but now, well, if we want to study more complex Broca stars, why we have to use this generalization? Well, the motivations come from the quantum point of view. There is a work, a recent work in 2023 from Miguel Cubier and collaborators in Mexico, where they study boson stars, scalar boson stars, in the context of semiclassical gravity. And this study shows that the L boson star configuration they showed at the beginning of this topic could be arised in a natural way, just considering one real quantum field, instead of putting by hand 2L+1 classical scalar field, classical complex scalar fields. So in that way, this system could be considered as a condensate of spin zero particles with the same energy and with the same angular momentum. So with this quantum motivation, we find important that extend the applicability of this generalization for the case of the Broca stars. Okay. Well, as a scientist, we have to be critical with our proposals. So the first question that we have to answer is if these objects could exist in nature. So the first question, well, the question that derives from this is that if these L Broca stars are dynamically stable. The first, let's look a little bit about L boson stars. In 2021, Nicolás Sánchez-Gual and collaborators showed that the L boson stars, that these are these particular multi-field objects with angular momentum for the case of a scalar field, have a privileged position in a family of multi-field and multi-frequency bosonic stars. They have the most symmetries of the system of this family, but as well, and most importantly, they are the unique solution for this family of bosonic stars. So it's interesting for us to try to test if these stability properties that, well, I mean for stability properties, that these objects are stable against perturbations in an kinetic way. So it's interesting for us to try to explore if these stability properties are presented as well in L Broca stars. Well, a recent result presenting almost two weeks ago changed a little bit the things, because in this result, Vallardero and Nicolás Sánchez-Gual and collaborators presented that the spherical Broca stars are not stable. In this plot, we can see that three families of Broca stars, and a spherical one, that is the black line, dipole one or prolate one, that is the red, and a quadrupole Broca star, that is the blue line. In this case, each point represents each configuration of these Broca star solutions. And we can see the curve with the solutions that have the less energy compared to the other solutions is the dipole prolate Broca star, this red curve. In that sense, in this work, they showed that the quadrupole Broca star and the monopole Broca star are not stable, and in fact, they migrate to states that are dipole or prolate. In this case, these new states are dipole in terms of the scalar Broca potential and prolate in terms of the energy density, as I'm going to show in these two videos that we can find YouTube. First, this video is about the energy density and the plane XC, and we can show that begins with a spherical form and then begins to oscillate and lose the spherical symmetry. To see the dipolar structure of this system, you can see again this spherical configuration of the Broca scalar potential, and then we see how loose the monopolar nature, and then change to a nature that seems, well, maybe it cannot be seen good here, but if we see here, we see the dipolar there and the oscillation with the dipole. Okay, so with this background of results, we're happy to announce some preliminary results about the L Broca star. In this case, L Broca star, what we found, we actually begin with some simulation, time simulation in the cluster of the University of Valencia. And we begin with the 2 Broca star, I mean the Broca star, the L Broca star with L equal to 2, because the case of L equal to 1 is not regular at the origin. We found initial data that present irregularity at the origin, so we discard that solution as bosonic stars and begin the simulation with this case with that L equal to 2. And in this case, the spherical harmonics that participate in this system are given by this image here. So we can see quadrupolar structures with L equal to 2 and M equal to 0, 1, and 2. And in these videos, I'm going to show first the energy density of the plane XY. That is spherically symmetric at the beginning. But after some time, it begins to degrade to another shape. It's something like a square-like toroidal shape. And oscillate around this toroidal shape. This result, what this result tells us is that the system is not stable. The L Broca stars are not stable. They migrate to a system that we guess that it could have axial symmetry. And to test that, we can see the plane XC that at the beginning is as well spherically symmetric, but then after some time, you can see a toroidal shape as well. This and oscillate around that. Okay. I don't know how much time I have. Well, all right. Well, basically, I can talk a bit about our future perspective. And first of all, with this solution that we found, we need to launch more evolutions, numerical evolutions of these configurations to see if these results are right, and try to explain them. When we characterize, when we will be sure that these solutions are right from the point of view of these numerical calculations, what we want to do is characterize these configurations and present them as a stable axially symmetric ground state of the 2 Broca stars. Then we are going to try to find some ansatz, like we do for the case of spherical symmetry at the beginning, to compare these numerical results with the analytical result that we can obtain with these ansatz. As I mentioned before, there is a well-motivated quantum generalization that we would like to study in the case of Broca stars, because we obtain the classical solutions of L-Broca stars. But we would like to work in the context of semi-classical gravity to try to show that the Broca stars in this context of semi-classical gravity can generate the L-Broca star solutions. And finally, we would like to explore numerically some astrophysical scenarios when we can form Broca stars. At the moment, there are some numerical results when we can put some clouds of dilute Broca fields and then releasing energy, the Broca star can be formed. But what we would like to do is try to propose some astrophysical scenarios when the black hole can be separated from the matter given by Broca fields around the black hole, maybe by a kick that can produce a pressure stripping, for example, and that is one of the ideas that we have now, and we are exploring in the bibliography to try to propose then numerical stories about it. Well, that's all that I have to say today. Thank you very much.
Thank you very much, Claudio. Is there any question?
Thank you. I have first one question about the simulations. Are you using spherical coordinates, Cartesian coordinates?
Cartesian coordinate.
Yeah,
we
okay.
use Einstein toolkit codes, basically. Yeah, maybe in our simulations we are afraid that can have some resolution errors because we have the frontiers of our box that were change the resolution of the grid that can introduce some errors for our system. That's why in the plane XY we can see this quadrupolar shape, square-like quadrupolar shape.
Yeah, because it was very pixel, and anyway, this square were too obvious. So I expect this may change or not, but I guess more resolution at least is needed to really be sure of. So
Yeah.
That was more a question, but we do what we can with the simulation, so it's okay to start with something. And then I have another question more about the more theoretical. So in the part where you include the angular behavior, so it's not like frequency, separate variables, frequency and radius, and you put this combination of the LM, angular, and so on. Yeah. So I am wondering about the derivatives. So why that particular combination of derivatives, and what is the impact of that particular combination of derivatives?
Okay. Well, as we can see for the case of L Boston star, is just enough to present these functions because what we wanted to obtain is a space-time that is a spherical symmetry. Okay, so with this matter function, we have a total tensor of energy momentum that is a spherical symmetry. In the case of L-Broca stars, to have energy momentum tensor with the same symmetry, it's just necessary to put these functions and even not propose these components. But when we try that ansatz, that is a natural extension of this to this, just putting the spherical harmonics, we found that the evolution equation and the constraints equations are not consistent each other. Because as we have here the time separated from this ansatz, when we apply this ansatz to the evolution equations, we lose the time dependency. So we have spatial equations from the evolution equation and constraints equations that are spatial equations as well, and they have some consistency between each other. So we begin to try what kind of variations of these spherical harmonics, and we found that with the derivative, we gain that consistency. And with the derivative and with this function R, VR. Yes.
And there is a question online. So Milton is asking if the square shape behavior could be due to numerical artifacts.
Yes, we think the same. As we work, well, we are going to try, well, now that the Luis Vives cluster opens again, because we know that is in maintaining works, we are going to put a bigger box to try to not have these errors that can cause from the different refinement levels. Okay, cannot be seen in our videos, but if we plot the first box, the frontiers of our box is almost at the most part of the star. So it's really close at the star, and that could generate that errors. So, but we are almost sure that these systems are stable because despite of these errors, the system do not collapse. When we see the minimum value of the lapse, we see a lapse that is changing in time monotonically, and then begins to oscillate, but oscillate in a way that behaves in the same form in all evolution. But we're almost sure that it's stable, but we have to clear all of these errors.
Okay, so let's thank Claudio again. The next talk, which is online, by Marco Aurelio Abreu Di Paula.
Hi, can you hear me?
Are you online? Yeah, I think we can hear you.
Yes, I will start to share my screen, okay?
Okay. Okay, hi Marco. Can you try to share your screen?
Yes, sure. Okay.
Okay, yeah, we can see it.
Okay. Can you hear me okay, or you need me to?
Yes, yeah, can hear you and see.
Okay.
So whenever you're ready, you can start.
Okay, Okay, so good morning or good afternoon to everyone. My name is Marco Aurelio, and I'm a doctoral student of the graduate program in physics from the Federal University of Pará. And today I'm going to talk about shadows and gravitational lensing of electrically charged irregular black holes in nonlinear electrodynamics. So this is the outline of my talk. I will start with a brief introduction about the subject. Then I will discuss the main topics associated with the presentation, and I will end this presentation with some concluding remarks. So before I start with the presentation itself, I just would like to point out that this presentation is mainly based on this work here that we published recently, electrically charged regular black holes in nonlinear electrodynamics, light ring shadows and gravitational lensing, which was done in collaboration with Dr. Haroldo Jr. and Pedro Cunha, and also with my advisor, Luis Carlos Bassalo Crispim. So we know that a general relativity is the best theory that we have to describe gravity so far, and we know this for several reasons, in particular due to the recent experimental developments in the string theory regime. We have, for instance, the gravitational waves, but we also have the shadows of supermassive black holes. But even so, we know that general relativity predicts at the core of standard black hole solutions the existence of curvature singularities. And the problem with such pathologies in this space-time is because at such pathologies, the known laws of physics break down. So, for instance, in other words, physical quantities like the energy or geometric quantities like the Krashen scale, they diverge at the curvature singularities. So there are several possible ways to try to circumvent to avoid the curvature singularity. One of the possibilities is try to obtain a fully quantum gravity theory, right? But so far, such a theory was not obtained fully compatible with gravities. But another possibility is try to obtain alternative theories of gravity. But there are also other possibilities, which is basically try to change the content of matter energy of the space-time. So for instance, this is the standard Einstein field equations in general relativity. So in the right side of this equation, we have the energy momentum tensor. And the main idea here is try to modify the content of matter energy to try to obtain charged regular black holes, which are basically black holes without curvature singularities, right? So these objects, they have very general properties that are very similar to standard black holes in general relativity. So if you focus, for instance, the spherical symmetric scenario, it's possible to obtain static and spherical symmetric spacetimes as solutions of the Einstein field equations. These solutions will be described only by mass and charge, and this charge could be electric or magnetic charge. And the causal structure of the spacetime is very similar to the standard black holes in VR in the sense that we still have a Cauchy and an event horizon, but the main difference is that in the regular black hole spacetime, we do not have such spacetimes do not have curvature singularities, right? So the thing is that, all right, you can change the content of matter energy, but what kind of possible physical sources are feasible in this setup? So there are several possibilities in the literature that we can try to use to obtain regular black holes as solutions of field equations. But here, one of the possibilities that we are going to explore is use nonlinear electrodynamics models. So I'm not going too much in details here, but the idea is that is basically to propose a nonlinear electrodynamic model for which, in the general scenario, for electrically charged black holes is given by this expression here. So what we actually need to specify here is the model of nonlinear electrodynamics, which is basically this function here, this structural function. And in the work that in this work, we choose to use the Irina Diminikova model, which we will call only by ID model from now on, for which the corresponding line element is given by the equation 1, where f of r is the metric function, and z is a function which depends on the electric charge and the mass of the black hole. One of the major results and one of the key results of nonlinear electrodynamics theories or models is the fact that according to such theories, photons follow new geodesics in the background of an effective geometry, which is different from the space-time for the standard geometry or space-time metric given by equation 1. We can actually show that for any electrically charged black hole obtained in the P framework, the effective geometry is given by the equation 3. So just to summarize, when we have a space-time based on nonlinear electrodynamics, massless particles with nature different than electromagnetic will follow new geodesics according to this expression here, G mu, K mu, K nu. So this is the case for massless particle, but for photons, we will have this expression here. So these P mu are new vectors with respect to the effective geometry, and P mu is related to the propagation of photons, while this other null vector here is associated with the propagation of massless particle. So the main goal of this work is try to quantify the effects of the effective geometry in the context of black hole physics, in attempts to review some inference of nonlinear electrodynamics theory in the context of black holes. So now let's focus on the main results. Let's start with the shadows and gravitational lensing. We know that in the spherically, if you consider the spherically symmetric case, for instance, we know that there is a boundary between absorbed and scattered geodesics, right? So, and this boundary is defined what we call by photon sphere, and this photon sphere, in the radius of this photon sphere is given by the critical impact parameter, which in this case here is given by BL. So we can actually show that for asymptotic observers, that is observers at infinity, the cubic impact parameter is actually equal to the shadow's radius given by this this letter here, RS. So by noting this, we can do a parametric plot of the photons here in order to obtain the shadows in the spherically symmetric case. Right, in this case, we obtain the edge of the shadows. So in this plot here, we show the shadows for different values of the normalized electric charge. The normalized electric charge is essentially the ratio between the electric charge to the extreme charge value. So as you can see, as you increase the values of Q, the shadows is diminishing, right? So another thing that we can try to explore is to see how the effective of course, this figure in the left here was obtained. We obtained this figure using the effective geometry as already discussed. So we can also try to explore what are the effects of the effective geometry in the shadows radius. And to do this, one of the possibilities is to plot the ratio between the shadows radius, considering the effective geometry where photons propagate, and the standard geometry. And by doing so, we can obtain this figure here in this other figure here, another figure here. So we can see that as we increase the normalized electric charge, the effective geometry can increase the size of the shadow up to 10%. And this means that when we are working with spacetimes associated with linear electrodynamics, we cannot, in general, ignore the effects of the effective geometry to compute the appropriate results for the propagation of photons. So we can also obtain the gravitational lensing associated with this spacetime. So here we have some examples of the shadows for the ID regular black hole, considering Q equals 0.3 in the left panel and Q equals 1 in the right panel. So there are some very interesting things to say about these figures. First of all, I will just briefly discuss how they are obtained. So essentially, we have a black hole surrounded by a celestial sphere. And we have an observer in the equatorial plane at a given distance from the black hole, and we use the backward ray tracing technique. So we basically evaluate the light rays from the observer position backwards in time to the celestial sphere, and then we can obtain such figures here. So as you can see, far from the black hole, far from the shadow's edge, the gravitational lensing of the two figures are pretty much the same, very similar. This is in accordance with our analytical results, but we can see that we have some interest difference in this shadow's edge, and we can also notice that as we increase the values of the normalized electric charge, the shadows they decrease, as we already showed before. Another very interesting results that we can obtain is what we call by fine-tuned degenerate shadows, which are the configurations for which a regular black hole can, a regular and a singular black hole can have the same shadow radius, which is basically to obtain such configurations, we just try to search for the values of the normalized electric charge for which the equation 6 holds. And for the ID regular black hole, we have this kind of configuration. So each circle here corresponds to a situation where the shadow radius of the ID and Heisenberg black holes are the same. Another thing that we studied in this work was it was an attempt to try to understand the effective geometry from a more fundamental perspective. So if we put an observer in this space-time metric and try to compute how the new vectors with respect the effective geometry behave with respect now to the standard geometry, we will obtain the equation 7. And this equation is telling us that for outside the event horizon, then photons will follow null or space-like paths according to an observer in the space-time metric. That means that from the perspective of an observer in the space-time metric, photons can propagate with a speed greater than massless particle or they will share the same light cone. They will share the same light cone to the massless particles. But the question is interesting related to this is the fact that we have shown that when we consider the shadow radius, considering the effect geometry, the shadow radius considering the effect geometry is always larger than the one considering only the space-time metric. So we expect that, but we are showing here in figure 7 that photons from the perspective of the space-time metric can propagate with a speed greater than massless particle. So we expect that photons will be more scattered since they are traveling faster than massless particles, right? But it's not that what happens. And the reason is that we can actually show that from the perspective of the space-time metric, we can understand the path of photons as if they were following no geodesic curve submit to a full force term as given by equation 8. And this force is some way somehow accelerating the photon. So to have a better idea of what is going on here, in this figure we show the path of a photon in a massless scalar particle for the extreme charge ID regular black hole, so K-1. So this continuous line here corresponds to the path followed by the photon, while the dashed blue line corresponds to the path followed by the massless particle, and this inner circle here corresponds to the event horizon. So as you can see, as the photon approaches the black hole, far from the black hole, the path followed by the massless particle and also by the photon basically the same. But as they approach to the black hole, the photon is absorbed by the black hole, while the massless particle is scattered. This happens because there is this radial force pushing the photon into the black hole, and that's why we observe that even though from the perspective of the space-time metric, photons can propagate with a speed greater than massless particle, the shadows of such scenarios is greater than from the massless particles. So now let's just move to the concluding remarks. In this work, we basically study electrically charged black holes in nonlinear electrodynamics. We focus on studying the shadows and gravitational lensing associated with such objects, and we choose a particular model. We work with the ID regular black hole solution. And for our perspective, this work is important basically, essentially for two reasons. The first one is the fact is the results associated with the gravitational lensing effects. So we have shown that the effective geometry increases the size of the shadow by almost 10%. So every time that we consider a space-time based on nonlinear electrodynamics, of course, it depends on the model, but our results suggest that we cannot just ignore the effects associated with the effective geometry. We also obtain that observers near the event horizon are strongly affected by the electromagnetic field. So as we have shown before, when a photon is approaching the black hole, he perceives a force associated with the electromagnetic field. And we also obtained what we call by fine-tuning degenerate shadows, which are the configurations for which a regular and a singular black hole can have the same shadow radius. For the point of view of the nonlinear electrodynamics, we have shown that the existence of a full force from the perspective of an observer in the space-time metric. As future perspectives, we are already working on and try to relate the causal structure of these spacetimes with the motion of photons, and we also trying to generalize the results to the effective geometry, considering more general net theory. So I have not talked about this in this presentation, but here essentially we consider models of nonlinear electrodynamics that depends only of one electromagnetic scalar. So we are trying to generalize the results for the effective geometry in terms of interpret the results in terms of full force, considering the scenario where we have the dependence of the two electromagnetic invariants. So that's all. just would like to thank the organizers for the opportunity to talk about my work. That's all. So I cannot hear anything. So I can hear you guys if someone says something. I'm not.
Oh,
Yes.
Okay, now I can. Yes, that's okay. Okay, now you are muted again.
yes. Okay, perfect.
Yes, now that's okay.
Okay, I was just curious because I saw you wrote at some point a certain static and spherically symmetric metric, but it wasn't clear to me whether that metric you wrote was a solution from an actual nonlinear electrodynamics. And if it is the case, could you show which is the theory? Maybe I missed it, but could you please show which is the theory for which that configuration is a solution?
Okay, if I'm not so sure if I understand your question, but you're asking to me what is the model that generate this black hole, right?
Yes.
Oh yes, I didn't put here the exactly model of nonlinear dynamics, but I can discuss some things about it. So yes, so to obtain exact solutions, we need to solve this equation here, right? The field equations with energy moment tensor with this kind of structure. So we need to impose a model of nonlinear dynamics. In this case, we use the model proposed by Irina Diminikova in 2004. I have not exhibited model itself, but there is a closed expression, which is actually a very simple one to deal with.
Okay, no, because I was just worried because in these theories, usually the charges that characterize the solutions already appear in the Lagrangian, and for me this is a technical issue. Yes, I was just curious if this issue also appears in this model. But okay.
Okay, yes, you have this kind of situations in nonlinear dynamics, but for the case of the Diminikova solution, we can actually this setup that I'm using here is already called by P framework, right? So you have this thing that when we look to the action, we have something that depends of the square root of a minus of negative scalar, right? But for geometries like the Diminikova solution, we can actually obtain the same black hole in the F framework where we do not have this kind of problems. So we can actually think in this setup that I use here as a trick to obtain the equations in a simpler manner. But you can actually try to obtain in a more correct scenario, let's put it this way, without any problem.
Thank you.
Okay, thank you very much. Maybe you can move on to the next speaker. So thank you very much, Marco, again.
Thank you.
Okay, so the next speaker is Sergio. Sergio, can you hear me? Are you online?
Hi, yes, can you hear me?
Yes. Yeah, okay.
Can you see my screen?
Yes. Let's see.
Okay.
Can you minimize the yeah. Thank you.
Okay, I'll do this. Oh, sorry. Okay.
Okay. Now we cannot see your. So whenever you are ready, start.
Okay, so first of all, I would like to thank the organizer for the opportunity to show my work here. And today we're going to discuss about this work that was published this year in Physical Review D and was done in collaboration with Dr. Haroldo Lima Jr. and Professor Crispino, which is my advisor, and both are from the Federal University of Pará in Brazil. And in this work, we have studied the gravitational lens of a toy model of a supermassive black hole surrounded by a dark matter halo. So I divided this presentation in three parts, where in the first part I will try to motivate the why to study this topic and try to introduce to you the space-time that you have analyzed. In the second part, we're going to discuss about the main results on gravitational lens that we have found, and I will end up with some final remarks. Okay, so we know that one of the major problems in modern astronomy is the dark matter problem, right? So we know that there are plenty of observational evidence for an unknown kind of matter that interacts only gravitationally and extends itself by beyond the luminous part of most of the galaxy, and which is the dark matter. And the observational evidence for dark matter comes from different scenarios, like the rotation curves of galaxy, weak gravitational lens, etc. But in these galactic scenarios, we have also another character which plays a major role, at least in the most active galaxies, which are supermassive black holes. And in fact, we already imaged one of these black holes, the black hole at the center of the M87 galaxy, and the black hole at the center of our own galaxy, Milky Way. And so in this work, we try to understand, okay, so since in these galaxy scenarios, there are this supermassive black hole, and they are surrounded by this huge cloud of dark matter. So is that possible that dark matter would imply some observational imprint on the gravitational lens of these black holes? And in order to try to get some insight on that question, we have studied a model that was first described in this paper here by Cardoso collaborators last year, where they have found a space-time of a black hole surrounded by a dark matter halo, an analytical solution of this equation, in fact. And in order to obtain that solution, they use a technique, a generalized version of a technique, which is called the Einstein cluster, which is basically a method to construct stationary system of gravitating mass. It's one of these mass moving along a circular geodesic about the center of the system under the influence of the gravitational fields of the other mass. And let me see. I was trying to I think now you can see. So to model this distribution of mass, they define this energy momentum tensor with a specific energy density profile, which is the Henkinski profile, which depends only on two parameters: the mass of the distribution of mass, and this A naught here, which is basically a length scale parameter. And with that energy momentum tensor, they could solve the Einstein's equation and obtain a static and spherical symmetric analytical solution, which depends on three parameters. Beyond that, parameters that I already told you, the mass of the dark matter halo and the length scale parameter, there is this capital MBH, which is the mass of the black hole. And in order to help us in separate the different scenarios or different configuration that this system can present, we're going to introduce this quantity here, which is the compactness of this system, which is defined like this. And basically what this quantity tells you is that if the compactness is much smaller than 1, it means that you are in a system with a very dilute dark matter halo. Whereas if the compactness is greater than 1, it means that you are in the dark matter halo is concentrated very close to the event horizon of the black hole. And you're gonna see in a few slides what are the implications of these two scenarios. So as I told you, we are interested in understanding how the light behaves around this black hole. And in order to do that, you must study the new geodesics, and you can follow a Hamiltonian approach, where basically you define the Hamiltonian of the new geodesic like this, and you can decompose this Hamiltonian a connected term plus a potential term. But notice that this potential term depends on the features of the particle, like the energy of the photon and its angular momentum. So it is interesting to introduce another function, which is this function h here, which is called the effective potential. And it is independent of the properties of the particle. And besides that, this function is interesting because the critical point of this function gives you the location of a very special class of orbits, null trajectories, that are called light rings. That is basically the photon circular orbits around the black hole. And you can have two kinds of light rings. The first one, which is associated with a maximum of this potential, is an unstable light ring, and is present in the most cases of the classical GR solution, like Schwarzschild and Kerr black hole, for instance. But beside one unstable light ring, we can have also configuration with multiple light rings, and also different natures, like for instance, a light ring associated with a minimum of the potential, which is a stable light ring. And when you have a configuration with multiple light rings, you can see that the gravitational lensing of this model, of the model can be very different. Here is a gravitational lensing of a Kerr black hole with a Proctor hair. So in the model that we have studied in this paper, we saw that in the regime of a small compactness, the potential is very similar to qualitatively similar to the case of Schwarzschild black hole, the vacuum solution of GR, and presents only one unstable light ring. However, when you go to high compactness regime, you can obtain solutions with more than one light ring, as indicated here by these red stars. So you can have a configuration with more than one light ring and stable light ring also. So, okay, what are the implications of this to the observational features, like for instance, the shadow of the black hole? So when in the case of static spherically symmetric space-time, as Marco Aurélio told us, the shadow of a black hole is basically the projection of the light ring in the observer planes of in the image of the observers of the observers. So in this small compacted regime, we have found that the shadow of this space-time is very close to the Schwarzschild shadow. In fact, the size of the shadow is very similar in this case. However, to the case of the high compactness regime, since now there are huge concentration of dark matter close to the event horizon, the size of the shadow is much larger when comparison with the case of the small compactness regime. Okay, but we also study, besides the shadow of this black hole, we study other features, like for instance, the gravitational lens. And the approach that we follow is very similar to what Marco showed in the previous presentation, that is basically consisting in considering as a source of illumination a celestial sphere, and then you put the black hole and the observer inside the celestial sphere and use the technical backward ray tracing that it basically is consistent and evolve numerically backward in time the light trajectories from the observer position to either be absorbed by the black hole, and in this case you assign it to the picture a dark pixel, or to be scattered to infinity, in this case reach the celestial sphere, where in this case you assign one of the 4 different colors of the grid. Okay, so just to have in mind, if there are no black holes between the observer and the screen, or between the observer and the celestial sphere, what the observer would see is something like this. However, if you put a black hole between the observer and the celestial sphere, since now the gravitational field of the black hole will distort the light rays trajectories, what you see is something like this, for instance, for the case of a Schwarzschild black hole. And now let's compare the case of Schwarzschild black hole with the case of the black hole with dark matter halo, but with the small compactness regime. And you can see that these two cases are very similar. Although there are differences here, this difference is very small. These differences are very small. But we can see that this difference increase as you go to the case of multiple light rings, since now the pattern of the length is changed, is very influenced by this regime of high compactness. Okay, but besides the length, one of the things that you can do is try to use the EHT data, the data from the Event Horizon Telescope collaboration, to put some constraints on the parameters of your solution. And there are at least two ways that you can do this based on the knowledge of the shadow radius. The first one is based on the idea that the errors of the measurements of the EHT are around 10%, which means that each pairs of values of the parameters of your solution that you are studying that produce a shadow radius that differs from the Schwarzschild-Oeckert case less than 10%, it means that with the actual precision of the EHT, the EHT cannot distinguish between this solution or a solution from GR, like a classical solution from GR, like Schwarzschild-Oeckert black hole. And with that, you can scan all the panels of the values of the mass of the dark matter halo and the length scale parameter, try to find if there are pairs that respect this boundary here. And here I show you two regimes. The first regime is when the mass of the dark matter halo is close to the mass of the black hole. And the secondary regime is when the mass of the dark matter halo is much larger than the mass of the black hole, which is the case for most of the galaxies. And this is the first approach. The second approach is based on the fact of a previous estimate of this quantity here, theta, which is the angular gravitational ratio. That is basically the ratio between the mass of the compact object at the center of the galaxy and the distance of this object from us. And with that, you can compute this quantity here, which is the deviation from the angular gravitational ratio as obtained by the EHT observation in comparison with this angular gravitational radius computed by other kinds of observation, like for instance, stellar dynamics. And remember that the EHT data are obtained with interferometry. So with this delta, you can compute this deviation, how much the estimate of the EHT observation are deviate from the previous estimates. And you can translate this deviation into bounds on the shadow radius of this compact object. And here is the case for the M87 star, which was the first image that EHT obtained. And basically what this means is that whatever pairs of values of these parameters that produce a shadow radius that is inside this interval here, in one sense, you can say that that geometry could explain the data of the EHT, or at least you can say that the EHT could not rule out that geometry with the current precision. So the green region in this plot shows what are these values. And here are the constraints obtained from the data from the black hole at the center of our own galaxy, right? The Sagittarius A stars. And there are two intervals here because there were two previous estimates of that comes from these two observatories, the Keck Observatory and the VLTI. And we can see from this plot that some configuration with high compactness, which present multiple light rings, are ruled out by the current EHT data. And to conclude, there are some future routes that you can follow after this work. So first of all, in this paper, we study analytical solution that was obtaining using a very specific profile to the dark matter, which is the Henkiste profile. And you could also investigate if there are more realistic profiles, such that the black hole solution with that profile would present multiple light rings in a small compactness regime. That's one of the routes that you can follow. Another things that you can do is, so in this paper, we have studied the shadow, which is basically associated with this static spherical symmetric case, is associated with the light rings. But you could also, and from this, we use the data from EHT to put constraints on the parameters of our solution. But you could also try to constrain the solution using, instead of the light rings, photon rings that are basically that unbound photon orbits that turns around the black hole several times. And this was done this year in this PRL, where the authors model a Kerr black hole where the dark matter halo around it was composed of a boson cloud. And they computed the deviation of the photon rings from what is expected from a Kerr black hole, they could put some constraint on the mass of the boson that compose this cloud. And so these are two main perspectives that you can do. And this is my knowledge, man. Thank you. That's it.
Thank you very much, Sergio. Is there any question? Okay, I have one. So sorry if I missed it, but so this second light ring, this table one, is coming from the dark matter component of the galaxy.
Yes.
So you're assuming that it's like some ultra compact halo.
Sorry, could you repeat?
You're assuming that it's an ultra compact halo to have this second light ring, or is it
Yeah.
like black hole with some bosonic pair, this kind of
Yeah.
hole?
In fact, this second light rings only appears when you are considering very compact halos. Yes. At least for this model here.
So, but also the profile of dark matter follows this kind of compactness when you are really close to the black hole. So you expect this second light ring, or is it something that you could see only in a few galaxies?
Okay, that's a good question, but from what we found here, I would say that if you are so if this is the standard scenario, I think you would expect a second light ring appears. But I'm not sure if you could say if this could be a general statement.
Okay, thank you very much. So, any further question? If not, let's thank the speaker again. The last speaker of the session is Zeus. Are you online? Can you hear me?
Can you hear me?
Yes.
I hope you can see my screen already.
Yes, we can. Can you put it in? Yeah.
Okay, may I start?
Yes, please.
Okay, thank you. Yeah, my name is Zeus Salles Moreira, and my presentation is entitled Quasi-Normal Mode Spectrum of a Schwarzschild Black Hole with Loop Quantum Corrections. This presentation is mainly based on my work that I've done in collaboration with Dr. Haroldo Lima Jr., Professor Luis Crispino, and Professor Carlos Herdeiro. We published this work in this year on PRLD. And yeah, I decided to start this presentation with a review of quasi-normal modes and one physical process that is of great importance to the study of quasi-normal modes is the coalescence of black holes. And the coalescence of a black hole binary can be basically divided in three main stages. So the first phase is called in spiral, and it represents the phase where the black holes are orbiting around each other, getting closer due to the loss of energy through gravitational waves. The second stage is called the merger, and it represents the actual collision of the black holes. And finally, we have the ring down, which is the phase where the remnant relaxes to its equilibrium stage, and it's losing energy through gravitational waves, and the signal emitted is dominated by the quasi-normal modes. And these quasi-normal modes carry information about the remnant, since the quasi-normal modes are fully determined by the black hole parameters. So these quasi-normal modes, the frequency of these modes can be generically divided in a real part, which is related to oscillation, and the imaginary part, which is related to damping. You can clump these frequencies all together in one single set. This set is called the spectrum. And in general, this set is discrete and infinite. Yeah, we organize the set as follows. So we call the fundamental modes the mode which with the smallest damping factor. That is to say, the smallest imaginary part in magnitude. And the modes with larger damping factors are called overtones. And to calculate quasi-normal modes, basically we have to solve an equation like this, which is a Schrödinger-like equation. This equation can represent scalar, electromagnetic, gravitational perturbations, and other types of field perturbations. And we also have to impose some boundary conditions. So we have to impose ingoing waves at the horizon, and we also have to impose outgoing waves at infinity. And here we are interested in studying scalar quasi-normal modes associated with this metric. So this metric was reported in this paper. I think it was published last year. So this metric is very similar to Schwarzschild metric. So here the GTT component is exactly the Schwarzschild GTT component. We have this function 1 minus 2m over r. But the GRR component have this new factor 1 minus r naught over r, where this r naught is a new parameter of the solution, which ranges from 0 to 2m, where 2m is the position of the horizon. So this metric basically represents an effective model of a Schwarzschild spacetime with corrections motivated by loop quantum gravity. And these corrections are holonomy corrections, and that's why this parameter R naught is called the holonomy parameter. Maybe I will also be referring to as the loop quantum parameter. Okay, so to describe scalar perturbations, we have to solve the Klein-Gordon equation. Here we are solving the massless Klein-Gordon equation. And due to the symmetries of the underlying spacetime, we can divide this scalar field capital phi in this form. So we have basically a function of the radial coordinate associated with the radial modes. We have the spherical harmonics and a factor of a time evolution factor. We can substitute this back into the Klein-Gordon equation and obtain an ordinary differential equation solely for the radial modes in this manner. So these are stars. Our star represents the tortoise coordinate, and this V, it's an effective potential given by this expression. So basically, we want to solve this equation for this potential, imposing the conditions of quasi-normal modes. As I said before, ingoing waves at the horizon, which are expressed in this part of the equation, and outgoing waves at infinity. Yeah, to solve this, to calculate the quasi-normal modes, I used three methods that were Bruni's method, Lever method, and also WKB. For time reasons, I won't explain them here. I will just put my results directly. So this first result, here in this panel on the left, we calculated the quasi-normal mode frequencies for the fundamental modes, which is displayed here in green. For the first overtone here in blue, and the second overtone here in red. We used WKB and Lever to make these calculations. So the circles represents the WKB approximation, and the continuous lines were obtained using the Lever method. The yellow circles represents the quasi-normal modes of the Schwarzschild black hole using the WKB method. So a first remark about this plot is that for L equals 0, the two methods don't agree very well. But as we increase the value of L, the two methods start to agree. This is related to the validity condition of the WKB, since the WKB is more accurate as we increase the value of L. A second remark is that the yellow circle, just stressing, the yellow circle represents the quasi-normal modes of Schwarzschild. So when we consider no holonomy correction, we are on the top of each segment. As we increase the value of the loop quantum parameter, we go down on each segment, and the general effect, at least on average, is to decrease the imaginary part in magnitude. So the modes become less damped. And there are two modes with a funny behavior that are the modes with N equals 1 and 2 for L equals 0. And I plot them here on the right so as to have a better look. So with no holonomy correction, we start on the top of the spiral. And as we increase the holonomy correction, we spiral down towards a fixed point in the complex plane, which represents the quasi-normal mode of the extremal case, that is the case where the parameter R0 is equal to 2m. And since these curves are self-intersecting curves, we can conclude that this spectrum is degenerate. So for different values of the holonomy parameter, for some given mode, we can have the same frequency. So here, we consider a plot of the first 30 overtones for L equals 0 of the quasi-normal modes of the scalar fields of the Schwarzschild black hole with holonomy corrections. So here, this plot's on the top left, represents a case where the holonomy correction is tiny, so it's very close to zero. And as we increase the holonomy correction, we have these other plots here. So for small holonomy corrections, the spectrum it's almost as Schwarzschild would be. But as we increase the holonomy correction, this wavy pattern appears. It's like a wave that goes along the imaginary axis, which is related with the possibility of having purely damped modes. We calculate this for L equals 0, but also we calculate this for L equals 1. And qualitatively, the effect is very similar. We also analyze the time profile of a Gaussian wave package that evolves over the space-time. We have to solve this equation. It's basically the same equation, but now we have this time evolution factor. And the results, our results can be seen in these two panels. So this panel, these panels are basically a log plot of the solution of that equation that I just showed you as a function of the time coordinate. And here we are fixing the radial coordinate at some fixed value. The plot on the left is for L equals 0, and the plot on the right is for L equals 1. We consider the Schwarzschild case in dark blue, and in the lighter blue, we consider the holonomy corrected case. And to analyze this plot, we have to divide the panels in 3 pieces. So this first piece on the left, it's for early time. It represents a early, a prompt response for the initial condition that we set. So it's basically defined in terms of the initial conditions that we choose. We have this at intermediate times. The signal is dominated by the quasi-normal modes, and at the end, for the late behavior is determined by a power law fall-off. And as we can see, the holonomy correction can only affect the part related to the quasi-normal modes. We also use the pruning method to extract from these time profiles the fundamental quasi-normal modes, and we compared with the other methods, and we obtained good agreement between the 3 methods. Okay, yeah, just going to finish here. Yeah, there is a summary of everything. I think I can skip that. I just would like to talk about future perspectives. So I think it would be nice to calculate gravitational quasi-normal modes of this space-time. Could also consider massive fields, but I think if I'm not mistaken, few days ago, someone already did it. And also we could explore rotating solutions with holonomy corrections. And yeah, that's all I have to say. Thank you.
Thank you very much, sir. Is there any question? Yes, Juan.
Thank you, Zeus, for your nice talk. I'm curious about the extremal case in the time domain profile when you have the late time tail that in your plots is like independent of the holonomy correction. Does this hold also in the extremal case when the ratio of R0 over the Schwarzschild radius is close to 1?
Yeah, this still holds. I mean, according to this model, you cannot consider exactly the extremal case. So the value of R0 is always less than 2n, right? But even if R0 is very close to the position of the horizon, this late time behavior it's the same. It's not modifying anything. So I just picked one value because I think would represent all the
okay.
It represents all the possible cases.
And the amplitudes are also similar, like this.
Yeah.
I see. And do you have any reason why there is it so robust? So so little difference with the pure Schwarzschild case?
Yeah, I mean, the main signature of the space-time, as I see, is contained in the quasi-normal mode. So, if you consider, for instance, Rice and Nordstrom space-time and Schwarzschild space-time, so they will differ also here in the middle, in the part where the signal is dominated by quasi-normal modes. But they will agree on the late time behavior. So it's harder in general to modify this part. So what I would argue is that the holonomic correction does not modify the potential enough to actually make a change here.
Okay, thank you. Thank you so much.
Okay, is there any further question? Yes. Yeah.
If we consider the black hole can create matter field, so what's the difference? Can you give a comment?
If we consider the black hole creating matter,
yes.
Yeah, I don't know. This is a vacuum solution. I have no insight to the case with matter around it.
I think in that will be more realistic. So I think if you study that, it will be more useful. Okay, thank you.
Okay, let's thank the speaker again.
Okay, so this is the end of the first day of the workshop. Thank you all for coming, for your interesting talks and questions, and for making it possible. And I hope to see you tomorrow here at the same time, 9:30, right? So enjoy the International Football League that we have today. And see you tomorrow. Thank you. I was